All right, let's dive in. Have you ever stopped and wondered how AI got so good at, well, language? We're about to go on a journey from what was basically a simple word counting trick all the way to AIs that can create entire worlds from just a few words. It's a pretty wild story. So let's get into the evolution of AI language models. Okay, so let's start with a little puzzle. Take a look at this sentence. Riyadh is the blank of Saudi Arabia. Now, for you and me, filling in that blank is a piece of cake, right? The answer, capital, just pops into our heads. But just for a second, think about it from a computer's perspective. This is a massive, massive challenge. How on earth do you teach a machine to understand not just the words, but the relationship between them? Well, the very first attempt to crack this code was basically just a prediction game. And it was built on an idea that's almost shockingly simple, just counting words. This gave us something called n-gram models. And, their simplicity is really their defining feature. An n-gram model just looks at the last word, or maybe the last couple of words, and asks a really basic question. Hey, based on all the millions of sentences I've read, what's the most probable word that comes next? So if it sees the phrase of Saudi, it's a pretty safe bet Arabia is coming next. It's all just a numbers game. But, and this is a huge but, there's a massive flaw in this plan. The model has absolutely no real memory. It just can't see the bigger picture. So in a longer sentence, an n-gram model gets totally lost. It only remembers the last couple of words, not who or what the sentence was about from the beginning. It completely lacks context. And so that set the stage for the next great challenge in AI, the quest for context. To get any smarter, these models desperately needed a memory. And that's where the recurrent neural network, or RNN, comes onto the scene. Now this was a big deal. The idea behind an RNN is to process a sentence one word at a time, sequentially, kind of like how we read. And as it goes, it keeps this running tally, this internal memory of everything it's seen so far. It's actively trying to remember the context as it moves along. But there's that but again, isn't there? The problem was the memory was just too short. RNNs have this Achilles heel called the vanishing gradient problem. The best way to think about it is like that game of telephone. You whisper a secret to the first person, and by the time it gets to the end of the line, the original message is completely warped or just gone. That's exactly what happens to the memory in an RNN. The farther back it tries to look, the fainter the signal gets. So yeah, it was an improvement for sure, but it still really struggled with long-term context. And that brings us to a landmark moment. The year is 2017, and a research paper drops with a title that sounds almost, bold. Attention is all you need. And let me tell you, this was not just another small step forward. This was a full-blown revolution. This was the birth of the transformer architecture, and it would change absolutely everything. So what was the big idea? Well, the absolutely crucial difference is how they look at a sentence. Remember how RNNs have to read one word at a time in a line? Transformers threw that whole idea out the window. Instead, they do something that sounds almost impossible. They look at all the words in a sentence at the exact same time. This parallel processing wasn't just about being faster, though it was way faster. The real breakthrough was that it let the model grasp the context of the entire sentence all at once. The secret sauce, the magic ingredient that makes this all work, is a mechanism called self-attention. Seriously, forget reading left to right. Self-attention is like giving the model a superpower. It can look at any word in the sentence and instantly connect it to every other word, weighing which ones are most important for understanding its meaning. It's building this intricate web of connections across the whole sentence. So in a simple phrase like the quick brown fox, when the model looks at the word brown, self-attention tells it to pay super close attention to quick and fox because, well, they belong together. It's basically creating this internal map of relationships for the entire sentence all at once. It's not just playing a guessing game anymore. It's actually starting to understand the underlying structure. Okay, so this is amazing, right? We've got this incredible new engine, the transformer, but even the best engine in the world is just a chunk of metal without fuel. So how do you fuel a transformer? How do you make it smart? Simple. You make it read. And I mean read a lot. This fire hose of information is a process called pre-training. And what we do is basically unleash the model on a huge, vast portion of the internet. We're talking books, articles, websites, you name it. And by just absorbing all of that text, it starts to learn. It picks up on grammar, on facts, on the subtle patterns of how we communicate,
all on its own. No one is sitting there teaching it rules. It's just figuring it all out from the raw data.
And this whole pre-training idea really split into two main approaches, two different philosophies, you could say. On one side, you've got models like BERT. BERT's whole game is to get really, really good at filling in the blanks, just like our Riyadh puzzle from the beginning. It uses a part of the transformer called the encoder, which lets it look at the words both before and after a blank space to make the best guess. Then, on the other side, you have models like GPT. GPT's goal is different. It just wants to predict the very next word in a sequence. It uses the decoder part, which can only see the words that came before. So you've got one that's a master of understanding deep context, and another that's a master of generating new text. But here's where the story takes a really fascinating turn, because this isn't just about text anymore. What we've really built is a kind of universal pattern recognizer.
So you might be thinking, okay, that's cool, but is all this amazing tech just for making better chatbots or helping me write emails?
The answer is a huge no. And this, to me, is the most mind-blowing part. The transformer architecture is just ridiculously good at finding patterns in any kind of sequence. It doesn't care if that sequence is words. It could be the sound waves of human speech, which is how we get speech recognition. It could be lines of computer code, which is how we get code generation. Heck, it could even be a sequence of stock market prices for forecasting financial data. The core idea is identical every single time. Find the pattern and predict what comes next.
And that brings us to the big takeaway here. Think about the journey we've been on. We started by simply counting words, and now we have a universal pattern-finding machine. What we've created is an engine for learning the logic of any sequence. So the truly profound question isn't just about what else it can do with language. It's much bigger than that. If this AI can master any sequence we throw at it, what patterns will it learn next?